So, now we are going to discuss design and development of incontinent products, needs and requirements in incontinent products. The first important need for all such products is absorption, because these products are supposed to absorb liquid. Hence, absorption is the most important property that these products should have. Then comes retention. In some of these products, retention is also very, very important. That is, the ability of the product to retain the liquid, so that it does not escape from the product whenever some external pressure is acting on it. So, that is absolutely very, very also equally important. Then comes a leak proof design, that is, whatever is absorbed, that remains within and it should not leak during actual use. The product has to be thin, and why thin? If the product is thin, it is very flexible, and therefore, it will be able to follow the contour of the human body. Therefore, thinner the product, better it is. Also, it can be stored very easily, you will require less space. So, that is also an important requirement. Then comes dry touch, that is, when it is wet, the wet sensation should not reach the skin. Otherwise, the person will feel very uncomfortable. It should give always a dry sensation, even though within the structure it is holding liquid. Conform to the body shape, that is also important, so that it does not look too bulky or too ugly. Should follow the contour of the body. It has to be soft in nature. Softness means that the person will feel comfortable. If something is very hard and remains in contact with the skin for a long time, then you feel irritated, and hence softness is another important requirement of it. Then lightweight. The lesser the weight, the better it is. So, these are the important. The last one is safety. Safety aspect is also very, very important, that whatever we make which is going to be used by human, and when it is used by children, we have to ensure that it has to be a safety angle point of view, it should be quite safe in use. It should not also create environmental pollution, that is also sometimes desired, and that has become a very important aspect in any product design. That is why disposability comes into the picture, that it should be easily disposable and it should get destroyed by the nature very fast, and it should not choke the drain, it should not create problem by any means with the environment. So, these are all the very, very important needs of any incontinence product, and keeping in mind these needs, the product design activity starts. Now, here in this particular slide, we are giving the need on one side, on one column, and the corresponding reasons are also stated. So, that we understand, already I have stated about it, but you should be able to understand it better, and hence it has been given in a concise format in the form of a table. Absorption, as I have already told, means to hold the liquid, and hence absorption is better. The more is the absorption capacity, the better it is. Second, as I said, retention, so that the liquid does not escape under pressure. Thin, why it should be thin? The reasons are stated here: ease of packing, flexibility, conformation to the body shape, and it should look decent. Leak proof, we have already said. Comfortable, and how to make the product comfortable? Softness is one important angle, and the other important angle is that it should feel dry, and hence, because these products are to be used for a prolonged time, especially if a person is old or a bedridden patient or a child. For them, it may be remaining with them for 4 hours, 5 hours, 6 hours. So, for such a long time, if something is there on your skin, it should be comfortable. Safety angle we have already stated. The other aspect is avoid rash formation. So, you have to see that the product should be to some extent breathable, so that the moisture vapor which is generated from the skin, that can escape from the skin. Otherwise, moisture will accumulate, there will be some kind of sweating, and it can lead to some kind of rash or itchiness could be there. Disposability, we have already stated that mainly to, so that it should not affect the environment. So, these are the reasons which are also stated. Now, we go to this slide, factors affecting the different needs. Now, if we look at these factors one by one, let us say absorption. Now, absorption depends upon what factors, because if we feel that absorption has to be enhanced, then we should know what are the various parameters which can be changed in order to enhance the absorption capacity. So, absorption typically depends upon the first of all type of fiber, that is the raw material itself. Then the parameter of the fiber itself, that is fineness, cross sectional shape of the fibers, and will also depend upon the property of the structure that we produce using these fibers, that is porosity of the medium. Whatever structure we make out of this fiber, either it is a non-woven structure or it could be a woven structure, it could be any shape. See, ultimately the fibers are to be given a specific shape in order to make a stable structure. So, that structural parameters where porosity and pore size, they become very, very important. Why? Because it is the pores within which the liquid is going to be retained or liquid is going to rest. And the other thing, that it is the capillary phenomena through which the liquid will move within the porous structure that we ultimately create using fibers. So, for the liquid movement, we have to create a porous structure, and through these pores the liquid will move and it will spread out over the entire part of the structure that we produce out of it. Therefore, these things depends upon, or all of them will affect the absorption. Next come retention. Retention depends upon also fiber parameters, fineness, cross sectional shape, the structural design the actual design of the structure as a whole, that is product as a whole, and it also depends upon the porosity of the medium and pore size. All of them will have a role to play on the retention part. Next comes leak proof, we have discussed. For leak proof, the important aspects are the retention capability of the fibrous structure as a whole. It depends upon the fit and flexibility of the structure, so that it starts leaking when there is some external pressure which acts on it. And the external pressure, if it is acting on a small area, the pressure is going to be very high, and in that case there is a possibility that the structure may fail. So, flexibility part of the structure as a whole is important, and how it is fitting. Even if some accidental leakage is there, the liquid should not move out. So, the fit between the incontinence product and the skin should also matter, so that it remains where it is supposed to be, it should not drip. The other aspects is also edge building. How do we build the edge of the product as a whole? We will see that one by one as we go through this. Then comes comfortability, as we have discussed. The importance of comfortable product is already discussed. So, if we say something has to be comfortable, then what are the important factors that we have to look into? One is one way liquid transport property of the top layer. If we think of a layered structure of the incontinence product, then you have to make sure that even under pressure, if we want to stop the liquid to move out of the absorbing medium, then we have to have some means to restrict the movement of the liquid outwards, even if some external pressure is acting on it. That means, if we can create a structure or as a design where there is one way liquid flow and the reverse flow has to be minimized. So, in one direction the flow has to be faster and quicker, so that whenever the liquid insult is there, it is get absorbed very fast, but whenever there is external pressure on it and there is a possibility of the liquid to put pressure on the entire structure as a whole, it will not be able to move, because we will have one way liquid transfer property that we want to create in the design itself. Then it will also depend upon fit and flexibility, so that unnecessary pressure does not develop at some corners on the skin. So, flexibility is important, the proper fit is also important, and overall softness is also very important. If it is not soft, if it is hard, or then because there is always going to be a friction between this product and the skin, and the skin area is very soft. So, if there is a friction between the skin and this product outer shell, there is a possibility that this continuous friction which will happen can create some kind of rash, or there will be readiness in the skin. So, therefore, it has to be very soft, and we have to make sure that the friction is very low between the skin and the outer shell of the product, the shell which will remain in contact with the skin, that part I am saying, not the really external part of the product which will not remain in contact which is visible to the from outside, but the inner part which remains in contact with the skin should also give you minimum friction between skin and the material that we use. Safety point of view, if you think about it, safety is a function of the leak proof design, antibacterial finish that we have given to it or not. Otherwise, the rash generation will be there, that could be bacterial attack. So, antibacterial finish could be of great help here, and one way liquid transport. So, that as I said it earlier, the reverse flow should be minimized. So, that even under pressure the amount of liquid, if at all something moves out, it should be minimized. So, these are the various factors. If the factors are there in our mind, then we can think of what we should do in order to satisfy the objectives or the requirements in the product. So, what we will discuss initially is ultimately this is a product where the major function is absorption. So, little bit idea about the absorption, I think we have already discussed in some previous lectures, but let us again look into it. Liquid absorption mechanism, what is important is wetting, transport of the liquid by capillary actions and by diffusion process. So, these are the basic important points regarding the liquid absorptions. The transportation of liquid within the structure is mainly through capillary phenomena, and capillary phenomena will only work when there are capillaries. That means, we have to have a fibrous structure where there are numerous capillaries exist, and the liquid can move through the capillaries. There has to be a network of capillaries. The other thing is diffusion. The diffusion means it happens at the molecular level, where the water molecule will penetrate the fibers and will occupy the space in the amorphous region of the fiber. Generally, the amount of liquid that goes inside the fiber, if we choose a fiber where there is a possibility of the liquid to penetrate the fiber, it has been seen that the diffusion, through diffusion whatever goes inside, that is much less in comparison to what remains within the pores of a fibrous structure. So, therefore, though through diffusion some liquid can enter, provided the liquid can penetrate the fiber. In some fibers it is possible, like water can easily penetrate cotton fiber, it can penetrate rayon fibers, but it cannot penetrate polyester fibers, it cannot penetrate polypropylene fibers. So, diffusion is not possible in those fibers, but it is possible in the case of cotton or rayon fibers or pulp, because they are cellulosic fibers and there is enough space available within the fiber, especially in the amorphous region, where the water molecule can easily go and stay. But even if it happens, the proportion of liquid that goes there is much less in comparison to what actually remains or flows into the pores of the structure made using millions of fibers. So, this is what is important, therefore, we should emphasize more on the creation of pores, so that there are space available between fibers to hold the liquid. Liquid is also retained within the pores. In case of external pressure, the liquid will remain within the pores. That is also due to capillary tensions. Now, physical phenomena responsible, this equation we all know, that is capillary pressure is 2 gamma cos theta by r, where gamma is the surface tension of the liquid, theta is the contact angle and r is the capillary radius. What is required is therefore, what a porous structure you have to create, so that the liquid can flow because of capillary pressure that is generated, and the magnitude of the capillary pressure depends upon these parameters gamma cos theta by r, where we do not have any control on gamma. Gamma is the surface tension of the liquid. If it is urine, whatever is the surface tension of the urine, that is the value of gamma, we have no control on that. Then comes the contact angle. Contact angle depends upon what fiber we have chosen. So, contact angle is depends on the raw material chosen, and therefore, depending upon need, we can choose the raw material. The other thing is the value of r, that is the capillary radius. This capillary radius is something depends upon the way we have created this structure. Now, from fibers we can create all types of structure that you are familiar with. A yarn is also a fibrous structure, a spun yarn. A fabric is also basically a fibrous structure, woven fabric, knitted fabric, because they are made from fibers, and these are basically different way of arranging fibers, and we have given them different names. Non-woven is also another way, another fibrous structure. So, whether it is yarn, whether it is woven fabric, whether knitted fabric, or whether it is a towel fabric, or it is a non-woven fabric, all are basically, in a way, they are all basically fibrous structures, and all of them will have pores between the fibers. Now, we have to choose a structure where pores are more, that is, we have to choose a structure where number of pores created by a given number of fibers is maximum. And the other thing is, what is the pore size? If the pores are very small in size, in liquid that will be retained within it will be also much less. If the pores are bigger in size, it will be able to hold more liquid. So, therefore, we need to know how to create a porous structure which will hold lot of liquid. So, two things are important: creation of a porous structure and the ability to hold the liquid within the pores even under pressure. Now, I were coming to a design architecture of incontinence product. If you look at it, a schematic diagram is shown here, and if you look at the diagram, this is layer number 1, this is layer number 2, this is layer number 3, this is layer number 4. That means, there are 4 layers. So, incontinent product will be having generally 4 layers. So, it is a layered assembly. Now, each layer has a specific function. The first layer is called acquisition layer. What is the function of this layer? That this layer is supposed to accept the liquid followed by immediate one way transmission to the next layer, which is called distribution layer. So, the purpose of the accumulation layer is that this layer has to be designed in such a way that it is going to accept the liquid when it is coming towards it, and it quickly transmit it to the next layer, which is called distribution layer. And the purpose of the distribution layer is to distribute the liquid over the entire surface of the third layer called absorbent layer. This is the layer, third layer, which is most important, because ultimately the liquid is going to be within this particular layer of fibers. So, absorbent layer is most important part of the design and plays the most significant role in the product performance. And below the absorbent layer, what we have? A barrier layer, that is impermeable layer to avoid leakage of the liquid under pressure. If the whole structure, this assembly is under pressure, then there is every possibility the liquid can escape through this, or it can move this way also. Now, how do we stop the movement downwards? So, if we have a barrier layer, that is a layer where there is no scope of the liquid to escape, it is an impermeable sheet. If we make it like that, then nothing can escape, no liquid can escape. So, the barrier layer has to be such that it is thin. Why thin? Because overall weight we should reduce. It should be impermeable, and the third thing is that it should not burst. It should have some strength, so that even under pressure, when the liquid exists within the absorbent layer and some pressure is applied in actual use, the liquid should not, this layer should not burst or should not tear. So, it should have some sufficient strength. These are the requirement for the barrier layer. So, keeping in mind these aspects, the function of the barrier layer, we have to decide which material we should choose here, which should be completely impermeable, thin, and at the same time strong enough to withstand the pressure which could be there during actual use. Because the patient who is having this, he can turn on the bed or he can sit on the bed. Same thing may happen with the child who may be jumping sometimes, sometimes the child may fall. So, there will be always, you can expect some additional external pressure that will be generated, and the structure as a whole should not burst out because of this external pressure, especially when the liquid is there within it. Then it will be a very messy affair. So, that is what we have to avoid. So, similarly, we have to avoid the liquid escape from the sides and liquid escape from the top layer side also, because liquid, once we apply some pressure in the liquid, liquid will try to find out a way to move out. So, whatever the way is there, it will flow along that particular path. So, we have to also seal it from side. That means, we have to seal from this side, we have to seal from this side. So, their sealing has to be done as well. And as I said, it is with the acquisition layer of the top two layers, here we have to play, because we have to make sure that the water or the fluid will move downwards, but will resist moving upward. It is just like a one way valve, that in one direction the valve will open, the liquid can flow, in the reverse direction the valve will close. Such a thing we have to create by using textile material. One way valve can be designed by the it has been designed by the mechanical engineers, but in our case that same concept we have to take, but point is what we should do so that the liquid flow, if we cannot stop the flow outwards from the top sheet, the flow can be minimized, because if we want to stop it we have to use impermeable material, and in that case the liquid will not move downwards also. Ultimately, first of all liquid will accumulate here when there is an insult, and then that liquid will flow downwards as shown by these arrows. So, this is very important to understand, and one should start thinking how and what can be done and how it can be achieved. Now, development of the absorbing core, first of all come the selection of fiber. So, we start with the development of the absorbent core first. Now, because it has to absorb, so we have to look for fibers which has good water absorption or moisture content, moisture regain properties are good. Now, here is a table where some data is there. So, we have to then consult the textbooks to find out which are the fibers which have good moisture regain. So, in that there are so many fibers in textile, you have already learnt about them. So, I have just taken few fibers, and we see cotton here, wool, viscose rayon, polyamide, polyester, acrylic, polypropylene and sap. What is sap? Sap is super absorbent polymer or fiber. It is super absorbent polymer. Fiber is also basically a polymer. Now, if we look at this fiber, exclude sap for the time being, what we see here that these are the potential candidates: cotton, wool, viscose rayon. Rest of the three fibers are not so good in terms of absorption, in the terms of moisture regain. So, we have to choose a fiber like this, but as we know that most of the material, most of the water will be retained by the by the pores. So, a porous structure can be created using polyester also. If we say argue that diffusion process, through diffusion process whatever goes inside a fiber is much less comparison to what remains within the pores. In that case one may say it does not matter, we can also choose polyester or acrylic, even if it does not absorb fiber water within it, the pores can be created and lot of water can be or liquid can be stored there. Yes, from this point of view it is okay, but there are other reasons also. The point is that anything that all these fibers, the cotton, wool and viscose rayon in this case, they show a contact angle which is very low. That means, wetting is very fast, liquid can easily wet these fibers. So, quick wetting is possible, whereas with this it will not be possible. And the second thing is the retention part also we have to take care of. You see the retention of the liquid under pressure, these values if we compare, these are on the lower side for these 3 fibers including polypropylene, whereas these fibers the retention of water is much better even under pressure, and therefore, because retention is also equally important in this case, and hence keeping in mind these two factors, one is are they capable to absorb themselves, can they absorb fast, and the second thing is what is the capability of the material of the structure as a whole to retain the water. So, there we find that this is the data which we could find out from some by doing some literature survey. So, such kind of literature survey, literature research is important when one has to design, and therefore, these are the potential fibers which can be used: cotton, wool, viscose rayon. Out of the 3, wool is very costly. So, why to use wool? And second thing is wool, fine wool is extremely costly, coarse wool is so coarse that it will pinch the skin. This is the problem with the wool, and wool absorb moisture, that is wool can easily absorb moisture in vapor state, but wool cannot easily absorb. The surface of the wool is hydrophobic in nature, the water will simply slide, whereas if it is in the form of a vapor, the wool fiber will be able to absorb it. So, these are the reasons why wool is not chosen. Cost is one reason. The second reason is if I go for cheaper wool, they are so coarse that they can penetrate the skin, and therefore, we can discard this. So, we are left with either cotton or viscose rayon. The other thing is what is also can be used is wood pulp, which is also basically cellulosic material. Ultimately, we are going towards a material which is cellulosic in nature, since cellulose can quickly absorb the water within itself through diffusion, and between them also whatever if there is some pores are there. So, suitable fibers are this. Sap also will come. Sap can absorb 400% of its weight, water can be retained. It will absorb water and it can retain also. So, sap is super absorbent polymer, this can be used, and this is also used to in some incontinence product they are used. We keep the quantity of super absorbent fiber maximum to the extent of 30% or 35%. The rest of the material will be either in some cellulosic fiber. But yes, sap has got some advantage, but we will see sap has got some disadvantage too. Okay. The next one is selection of fibrous structure. As I was telling that yarn or woven fabric, knitted fabric, towel fabric or any other fabric for that matter, and non-woven fabrics, all of them are basically fibrous structure. So, which structure we should choose? One is we have to keep in mind liquid absorption capacity of the structure, liquid retention capability of the structure, and deformation resistance capability. These are the 3 things we have to keep in mind while deciding the fibrous structure. Liquid absorption capacity. Some liquid is absorbed within the fiber through diffusion, we have already discussed it, and the rest of the liquid is absorbed within the pores of the textile structure. So, whether it is yarn, the pores are there between fibers and the yarns are converted to fabric. So, pores are there within the yarn and that could be some space available between the yarns to hold some liquid also. And if it is a non-woven material, then there are lots of pores between the fibers. Now, pore volume is volume of the structure minus volume of the fiber. Generally, we use non-woven type of structure for such kind of applications, because non-wovens, first of all, it is very nice process where fibers can be transformed into a medium which can absorb very fast. We need not to go through a long process of converting fiber to yarn, then we have to make the fabric, going through so many stages. So, all those stages can be avoided, there is no need to do that. Directly we can make an assembly of fibers using a non-woven line, and there are many techniques of non-woven, but some of the technologies are suitable for cotton or rayon, we can use them. So, from the theory point of view, the pore volume is the volume of the structure as a whole and the volume of the fiber. So, pore volume per unit mass of fibrous structure is volume of the structure divided by weight of it, the volume of the fiber and the weight of the fiber, we divide it. So, we can write pore volume per unit mass C is A T by W. What is A, what is T are all stated here. A is the area, T is the thickness and W is the weight of it. So, if we think of a rectangular structure of non-woven, then A T becomes the volume and W is the weight of it. So, A T by W becomes the total volume of the structure as a whole. That means, we are thinking that we have a assembly of fibers which is rectangular like this, and it consists of lot of fibers. And what is this? This is what is your T, and this total area of this is actually A. So, A into T becomes your volume, and now this becomes your volume of fiber per mass, that becomes basically means 1 upon mass per volume. So, that becomes reverse of this is basically density of the fiber, and hence it is 1 upon rho f, and therefore, it is an A T by W in a way. If A T we bring it in the denominator, then it becomes W by A T, and that is what is the density of fabric. So, 1 upon rho of fabric, 1 upon rho of fiber, and this is density of fabric and density of fiber are related by this formula, that is rho of fabric is rho of fiber into packing coefficient of fibers within the structure, and therefore, we can write this is the porosity of the structure, this phi, and hence this is the formula that is on which the pore volume per unit mass will depend. So, how much pore volume is there per unit mass of the fiber? Because if I can create more pore volume per unit mass, I will have more space available for liquid to be there, to remain there. So, therefore, what matters finally is two important parameters, that is density of the fibers and the value of psi, that is fabric porosity. Fiber density depends upon whatever fiber we choose. Once we choose the fiber, the density is fixed, but what is in our hand is the fabric porosity part. porosity will be decided by the process of manufacturing. When you manufacture a, suppose in this case a non-urban structure, then we can adjust the process parameters, so that we get the desired porosity. So, porosity versus process parameters, this needs to be then established in order to create or to produce something which will show you a particular value of porosity. This is very important. The other thing is that was most important in this case, and the structure as a whole should also have some strength, not very flimsy type of assembly of fibers. It should have some minimum strength, then we can handle it. If it is just loose assembly of fibers, then mechanically carrying the fiber to one place to another place or to convert it into a product will be very difficult. So, there has to be some amount of strength, which we can have by some techniques. There are many techniques by which we can enhance the strength of an assembly of fibers. Needling is one technique is there, there are other techniques also. So, anyway, that is something which we are not going to discuss. Fibrous structure suitable for absorption, if we go, which I have already discussed, oven is not suitable because of low porosity. Knitted is not suitable because of low also porosity. Non-oven suitable because porosity is high. Typically, non-ovens will have porosity 0.7 to 0.95. This we can study from the literature, that commercial non-oven which are available, they can have porosity value starting from 0.7 to 0.95. 0.95 is a very porous structure, 0.7 is quite tight structured. And we can have loose fibrous mats also suitable, which could be porosity is also high, as loose assembly of fibers. Like wood pulp, which is used in the commercial products, is just an assembly of a powder like assembly, and it is very loose in nature. So, by itself it has hardly no strength at all. So, the manufacturing technique has been designed in such a way that such kind of wood pulp can be used. But so therefore, either this or non-oven, both can be used. Absorption capacity wise of non-oven structure, some data are given here just for your sake of understanding, that capacity of cellulose acetate, triolable rayon, polypropylene. Some people have done some research. These are the data collected from scanning some research articles. So, it gives some idea, the capacity could be 18.6 cc per gram for cellulose acetate, triolable rayon, polypropylene, cotton, polyester. The rate of flow cc per gram second, these values are also quoted here. So, you can see here that these are the typical values that have been shown in some literature, while they have used a wave GSM varying from 40 to 120, needle density 80 per centimeter square, and fiber fineness used 3 denier. Enhancement or absorption by incorporating now superabsorbent fiber. We have discussed earlier, we have seen that superabsorbent polymers can absorb lot of water, and it can retain also lot of water. So, people therefore, also have tried, or even it is there in commercial products also. So, you can think of using superabsorbent fibers, but you see superabsorbent fiber, the two diagram that is shown here, this side is percentage of superabsorbent and this is the absorption capacity. and here is the percentage super absorbent and this is the rate graph. So, we say as we increase the content of super absorbent in the mixture, the absorption rate goes down, while absorbent capacity goes up. So, the more you add, capacity will rise, but rate will go down. The rate goes down, then after insult the water is not going to penetrate within the structure faster, it will slow down, and therefore liquid will accumulate and it will remain in contact with the skin. That danger is there. So, therefore, you have to be very cautious about using the super absorbent fiber, especially the quantity of the super absorbent fiber, that it decreases in absorbency rate, though it can increase absorbent capacity. The super absorbent polymer, once it absorbs some water, or so it transforms itself, it becomes a viscous liquid. The polymer itself completely disintegrates and it will be now behave like a viscous liquid. And what happens, that it can block many pores as a result of that, and therefore, if I use too much of this super absorbent fiber, the water wall capacity may go down also, because it will block many pores and will not allow the other fibers to absorb, because it is blocking. That is the danger with this, because it transforms itself into viscous liquid. Under pressure, this liquid will not move so easily, because its viscosity has become very high in comparison to the water. So, the water get mixed up. If the super absorbent polymer, the polymer changes itself into a viscous liquid, and the liquid will not be able to flow so easily. The way water flows, the super absorbent, this viscous liquid will not flow so fast. Therefore, it can hold the liquid very easily without leakage. That is the advantage we get, and hence one has to very judiciously use the percentage of super absorbent fiber. So, that way we need to use them. Now, liquid retention under pressure, some data we could see, and they are all given here. Retention under centrifuge data could be seen, these values are stated here, and the surface energy of some of these fibers also stated here. So, retention capability depends upon nature of the fiber, it depends upon deformability of the structure. How the structure, that is, if it is non-woven, how deformable it is? Does it get compressed easily by applying little bit of pressure, or it resists deformation? This will depend upon the bending rigidity of the fibers. Depends upon, therefore, on the coarseness of the fiber that is used. So, when the structure is relatively rigid, because maybe we have used, suppose somebody uses coarser fibers, then deformation will not be easy, and therefore, under pressure it deforms less. Therefore, lot of space will be still available for liquid to be retained. If I press it and wherever pores will get pressed, then the liquid will escape, try to escape from those pores. But if the pore get compressed less, because the structure as a whole is not really deforming much, since it is much more rigid, in that case the retention will be more. So, therefore, deformability of the structure is important, ability of the fiber, the polymer, to transform itself into viscous liquid, as I said in the case of sap, that is what happens. Rest of the fibers will not change, they can at the most change their diameter. Viscose rayon, cotton or pulp has been seen that by absorbing water, because the diffusion of water within the structure, individually the fibers become little bigger in terms of diameter, but this is not going to happen with acetate or polypropylene or such kind of fibers. The other thing is capillary size. Capillary size can be controlled by choosing the fiber parameters and the structural parameter of the, if it is non-woven or non-woven. Fiber parameters, what are important? One is the diameter of the fiber, the other thing is cross sectional shape of the fiber, the third thing is crimp in the fiber. All of them will affect the pores and therefore, the capillary size, everything will depend upon what is the diameter of the fiber, what cross sectional shape it has, and whether crimp is there or not. All of them will affect the capillary size. And then the structure that you have produced, how stable the structure is, if it is non-woven, how much punching we have done in order to create entanglement between the fibers, so that they get consolidated. So, all these will basically decide the capillary size, which basically is a function of such parameters. Then comes the external pressure that we apply. If the pressure is less, more liquid will be retained. If the pressure is more, less liquid will be retained. That is how liquid retention will change. And fibers with high surface energy can hold more water. They will not allow the water to move out from the capillaries so easily. They will create resistance to the movement of the liquid flow. So, that way the cotton has an advantage. Suppose if we use polypropylene, polypropylene will be able to absorb, polypropylene non-woven can absorb some liquid, but if we put little pressure, most of the liquid will flow away. Like sponge themselves can absorb, but after absorption, if you will put little bit of pressure, most of the liquid moves away from the sponge, and the smaller the capillary, better would be the resistance. This is good in a way, but smaller capillary would means small diameter fibers, but small diameter fiber again problem is they are so flexible that the woven, the structure as a whole will be so flexible that they can get, now deformation of the structure will be very easy if it is made from fine fibers. Anyway, fine fibers are costly, so there is a cost wise also they are not suitable. If I use them thinking that I will try to improve the retention power of the capillaries, with finer capillaries can only be made from fine fibers, but then the structure deformability is going to increase, and therefore, under a given pressure it will deform more, and therefore, the pore space available in a deformed state will be much less, and therefore, most of the liquid will flow out. These problems are there, and we have to strike a balance. We need flexible structure, we also have to see that it is going to retain the liquid, it is going to absorb the liquid. So, there are demands on the properties of the structure as a whole, where some of them may be conflicting in nature, and therefore, we have to strike a balance. Now, we come to the shape and size of the product. So, typically this incontinence products shape looks like this as shown in the diagram. It is a bow shape, narrow at the middle here and wide at the edges. The shape facilitates leg movement. This kind of shape is chosen so that leg movement becomes easy. That is why such a shape is chosen, and with the widened front and back, this side and this side that you see it here, allows more absorbing fiber mass to be accommodated over a larger area. Ultimately, if this is the space available as shown in the diagram for the absorbing medium, then if it is wider this side, front side and back side, then larger surface area is there. So, more fibers can be accommodated. More fibers mean overall absorbing capacity of the structure is going to be more. So, more the fibers, more will be the capacity. So, therefore, this kind of shape is actually chosen, and typical the size of a structure is shown here. Typically, the length is 30 centimeter and the width is 10 centimeter. This is the typical diaper of a baby, not for an adult, for a child. This is the typical size. Structure development of the components. Say if we want to see how do I develop different component, the acquisition layer, the requirement is quickly allow the liquid to pass to the next layer, promote one way transport of liquid. It has to be soft and hydrophobic because it is next to the skin of a child or baby, minimum or no re-wet under external pressure. Recent developments are therefore multiple layers as acquisition layer and density and capillary gradients. That is what has been done. I will show you that this is what one is, that you create the acquisition layer in such a way that you have large pores and small pores, that is you have gradient, so that you can create a capillary gradient. So, that idea is through that the liquid can easily enter from top. If this is basically the top sheet, or people have developed such kind of structure also, that a fabric where one face is hydrophobic, the other face could be hydrophilic, or it could be a thin layer, a hydrophobic layer and a hydrophilic layer. This also can be done. The option B is, I will come to that now, development of distribution layer. There are two ways we can do it. See, first layer is basically to accept the liquid as it is coming out with a certain force, and then immediately pass it to the next layer. And if it goes to the next layer, it is better that if it is distributed, so that the entire absorbing area participates in absorption immediately. And therefore, what we need, the second layer is a distribution layer. So, distribution layer if we want, then one is hydrophobic and hydrophilic stripes can be incorporated like this. Hydrophobic stripes will quickly disperse the liquid. As the liquid comes over it, it will immediately flow to the hydrophilic side, and through that it can easily spread out this direction and this direction, it will move very fast, and therefore, and below that the absorbing medium exists. In this is what is the stripe pattern is generally can be used, or sometimes what we can do that is not generally done. In this case generally if it is a distribution layer, this is what is done. One can also introduce some, but that is what is done in the case of the acquisition layer. The acquisition layer, sometimes this is in some design it could be only a single layer instead of two layer, and therefore, the acquisition layer also acts as a distribution layer. That kind of design is also possible. The idea is it should be able to accept the liquid as it is coming and quickly transfer to the absorbing medium, and it will be distributed over the entire absorbing medium. So, that the absorbing medium can absorb it very fast. Keeping in mind this objective, we have to think of the design. Option B is dense structure made from fine fiber, so that distribution is faster due to high capillary pressure. So, that is also can be done, but dense structure can make the liquid penetration difficult, hence optimum fiber packing is required. Generally, this is what is followed. Stripe patterns could be there, and there are different types of pattern could be there. That is, you basically have hydrophilic and hydrophobic regions. So, from hydrophobic regions, it will the liquid will be immediately flowing towards the hydrophilic regions. In this case, all these white regions are basically hydrophilic, and they act as a channel, and the liquid will be immediately transmitted, or it will spread over a larger area, and just below this we have the absorbing core. The real absorbing core is just below it. Now, we are going to find out, for example, how much material is required for absorbing core. Let us say we have to manage the urine discharge by a baby's typically 12 times a day and 30 milliliter per insult. So, solution is in 6 hours, the fluid accumulation in 6 hours is going to be 3 into 30, that is 90 ml or 90 gram. Now, to absorb this 90 gram of liquid or 90 ml of liquid, assuming that the density of this liquid is 1. So, we say 90 ml basically means 90 gram. So, typical cotton wave absorption capacity is 14 gram per gram. This data will be available from literature, and if it is this, so cotton required to absorb 90 gram of liquid is 6.4 gram, that means. Okay. Now, let the size of the absorbent core is 30 by 10, because we have seen the total size of this typical size, especially length and breadth of a diaper. So, typically it could be, let us say 30 into 10, 300 centimeter square, is 0.03 meter square, assuming that it is just a rectangular piece. So, let us say to make the calculation simple, we are not really taking the bow shape into account. Let us assume that this is a simple rectangular piece of fabric, non-absorbent fabric, which is going to absorb the liquid. So, it is basically the absorbing medium is like this. So, required GSM of the fabric is going to be 6.4 by 0.03, that is 213 gram per meter square. That should be the GSM of this non-woven material that we are going to use. Out of this now comes that actual GSM requirement will be required GSM multiplied by a factor of safety. Why factor of safety? Because you are going to make a product and you do not know that the actual user discharge may vary from person to person. And then we also want that the absorbing medium should not be saturated with the liquid. So, we to be on the safe side, it is better that we use a factor of safety to take care of these aspects, and maybe the entire area which is 10 by 30, all of it may not participate in absorbing, maybe the absorption part is from here to there, only this much, let us say, only absorbs, the rest of the material may remain dry, but the material is available there. Hence, keeping in all these factors you have to keep in mind when we actually designing a practical item comes. So, we take a factor of safety which is 3 times, and that becomes my actual GSM of the absorbing core around 640 gram per meter square. So, reasons of safety factors is already stated here. All the path of diaper may not get fully utilized for absorbing the liquid. Liquid insult and its frequency may vary from person to person. You want to satisfy, a design must satisfy a large segment of the customer, and therefore, that is what is the, this is going to be the GSM around 600 gram per meter square, only GSM of the absorbent core. So, it is just a typical case. The other thing now will come, possible reduction in weight of the absorbing core. Now, if you think of reducing the weight of the core, if we feel that by having such a GSM it becomes too heavy or it be too thick in nature, then obviously people think of reducing the weight. So, one of the way to reducing the GSM is by incorporating SAF, super absorbent fiber or super absorbent polymer, whatever you say, we can use them to the extent of 10 to 20%, because we have seen that from the research that too much of use reduces the absorbency rate, because it immediately transforms into a viscous liquid and blocks many pores. So, that is the danger, that too much of it should not be used, little bit of it 10%, 20% or maximum 30% can be used. It will reduce the overall thickness of the diaper and it will make it lean. So, we can think that if I use so much gram, how much liquid it can absorb, and rest of the absorption can be passed on to the other material, which could be cotton or which could be wood pulp, whatever it is. In the leak proof design which we are discussing, this is the typical a simple sketch of the design, one cross sectional view. What we have here, the structure has to be covered and sealed to avoid leakage. Now, this is the part where the core is, absorbent core is shown here. Then we have the barrier sheet as shown here, this sheet is the barrier sheet, that means it is impermeable. So, nothing will, this is what the sheet which will be visible and liquid will not be able to pass through it, because it is completely impermeable. Inside you have this absorbent core and acquisition layer, distribution layer, everything is inside. Now, the other side, the top part of it is actually so we have a non-woven sheet as shown is here. So, barrier sheet at the bottom is impermeable, placed at the bottom. Generally thin plastic sheet like polyethylene sheet can be used there. Top sheet is hydrophobic in nature, allowing one way transmission of the liquid, this one, this is the top sheet. We want one way liquid transmission. So, that has to be kept in mind, keeping in mind if we have a hydrophobic in nature allowing one way transmission of liquid. See what happens, that if we have two layers, porous layer, one is hydrophobic and the other one is hydrophilic. Then if I drop some liquid on the hydrophobic layer, the liquid will easily pass through it and will be absorbed by the hydrophilic layer, which is at the bottom. So, hydrophobic to hydrophilic, this movement could be one way movement. So, the way to create such a one way movement is either you make it a completely hydrophobic, but also must have pores, because it is through the pores that the liquid will enter. But because just below it the absorbing core exists, it will be immediately absorb the liquid, and this differential the difference in the, you should say, the surface energy of the material which is there in the core and is also on the top sheet will always create a one way transport of the liquid from top to bottom. So, coated non-woven with top side hydrophobic in nature also can be used. So, there are many types of designs are there. This sheet also can have some macro holes also could be there. So, that through these holes the liquid can enter very fast, but then there is a possibility of also the reverse flow, but reverse flow has to be stopped by having another as I said distribution layer could be there. So, there are different types of design that is possible here, which people can think of, many ideas may come, but the moot point is we allow the liquid to go from top to bottom side, but will not allow them to move from bottom to top, neither they should leave from the side. So, therefore, from the side also they are all basically completely covered, so that there is no leakage from the side also. And then we have to seal all the edges, and generally heat sealing is done. That means, the material which is used for the top and the bottom sheet, they should be able to melt under a certain temperature, so that we can heat seal them. So, that way you have to choose the polymer for the top sheet and for the barrier sheet. And then we have the other fastening devices like elastic leg, tape, all these things, so as to tighten it, that and the stand up elastic ensured snug fitting of the body contours. So, the elastic bands are there, we can adjust and can really make a very snug fitting of the structure. This is basically it is a diaper structure, and that can be used. So, this is a nutshell in a very we are discussing the design aspect of the incontinence product, and this is what is normally practiced. And now one can really think of improving the design further to satisfy the need of people of different ages. We have different sizes. So, obviously, one size does not fit all. So, depending upon the age of the person, we can have different size, small, medium, large, extra large, all sort of things is possible. So, anyway, with this particular topic is over now, and in the next class we will discuss about some other design. Okay? Thank you.